influences the existence of rational points. So here's the theorem of Legendre. So C has points everywhere locally, and I will sort of routinely include real numbers into this, if and only if there's a rational point. And if you have a rational point in a conic, it is isomorphic to the projective line, and so you can parameterize it with rational functions in one variable, and then you can approximate any finite so if you're given a finite number of primes, and maybe also real points, so you can approximate p-adic points with a rational point. So that's weak approximation. So so we have, in this case, weak approximation. Now let me consider a generalization of this. So let's write this equation. So it's a Diophantine equation with rational coefficients, and it describes a family of conics, a one-parameter family of conics. So T is a variable, and the i's are some rational numbers which are pairwise different. So let's think about this surface as a closed subset of P2 across the affine line. So the affine line has variable t, and P2 has homogeneous coordinates x, y, and z. And we can always arrange by change of variables that n is odd. So that we simplify an assumption. It's not really an assumption. So without loss of generality, you can assume n odd. And then it'll be more convenient to work with a projective, smooth and projective. So x will be a smooth and projective surface, which is a computation of y, smooth projective computation of y. And this is a family of conics over the projective line. So we essentially just add one more fiber at infinity. Okay? And because I assume n is odd, the fiber at infinity is going to be singular. So it will be a degenerate conic consisting of two components defined over a quadratic extension obtained by joining to q square root of a. Okay. So total number of degenerate fibers is going to be n plus 1. So the Diophantine problem here is that clearly we have rational points on this surface. So there are obvious points like 0, 0, 1, and then t equal to ei. So there are finitely many of those obvious points. And the question is, are there any others? So are there more pure rational points? For instance, are rational points Zariski dense? And even a stronger question would be, do we have weak approximation, and if yes, then in what sense? In what sense precisely? So I'll start with the strongest question. So there's an obvious restriction. There's an obvious condition that must be satisfied by a family of periodic points in order to in order that the rational point that approximates this family could exist. So this is coming from the classes in the Brauer group. So the Brauer group of X defined by Grothendieck is the second italic homology group. But okay, I will not use this description. I will work with. So Grothendieck proved that this is naturally a subgroup of the function field, characterized by the property that residues are trivial. Now, I will not go into this. I mean, I just want to work with explicit Brauer classes coming from these factors on the right-hand side. So consider the quaternion algebra and the class defined by the quaternion algebra in the Brauer group, namely. So think about this symbol. Okay, so it's a class of the quaternion algebra in the Brauer group of the function field on the base. And we would like to lift it. So let me call this morphism pi. So I want to consider the inverse image of this class in a Brauer group of a function field of X. And it turns out that this is in fact an element of the Brauer group of X. So the residues are all trivial. And in fact, this follows from the equation. So the equation says immediately that we have the following relation in the Brauer group of Q of X. Okay, so they, if you have a symbol such that one of the sort of constituent elements here is a norm, so if this is a norm for the quadratic extension given by square root of A, then the symbol is 0. So using this fact, we have this relation in the Brauer group of Q of X, and so somehow we can always replace. So, for example, if t equals the I, we can replace this symbol by the sum of all other symbols plus this constant element. So this immediately shows that I can sort of replace this by just a Brauer group of X. So it's a subgroup of Brauer group Q of X. So I mean, I calculate all the residues and I check that they're all equal to 0. So we get some element in the Brauer group of X, and by functoriality of the Brauer group, we can evaluate this element at any point. So in particular, if I have a collection of points PV, where V is a place of Q, so it's either periodic field or real field, then I'm looking at this Hilbert symbols for each V. So that's the usual Hilbert symbol. And a moment's reflection will show that, in fact, only finitely many, so there are only finitely many V's for which this is different from 1. So this could be plus or minus 1. So this is minus 1 for only finitely many V's. Now that's a good reduction argument. You just need to include, you can throw away all the bad primes, all the primes you don't like. The primes that divide A, B, and differences of EI and DJ, and a sort of short valuation argument will show you that this is in fact 1 outside of finitely many places. So it makes sense to consider the product of these plus minus 1s. So this is just an element of plus minus 1. And I'm taking product for all places V. And if my family can be approximated by a rational point. So by continuity, this must be equal to 1 by the product formula for the Hilbert symbol. So there are some necessary conditions that must be satisfied in order for these p-adic points given by sort of PVs for all V to be in the closure of the set of rational points inside the adelic space. So I'm talking about this inclusion. Okay, so this is the topological space with the product topology coming from natural topology, p-adic topologies in each x of QV, and the image of a set of rational points is contained in the closed subset of this topological space given by such conditions. Well, this is a down-to-earth description. In fact, this is a particular case of the Brauer-Manin obstruction. Right, so this is an example of a Brauer-Manin obstruction. Or should I say the Brauer-Manin obstruction? Given by this Brauer class. Okay, I think you can. What did I say? Well, I say this is an example. This is an example, and then I decided to make a longer sentence and say exactly how it works. Yeah. No, I mean it's well defined. So once you get a class, once you have a class in the Brauer group of X, then there's a condition like this coming from this class. So you can, I think, starting from this, you can somehow see exactly what's the general definition of Brauer-Manin obstruction. So if you have any class in the Brauer group of X, and you have an adelic point, you can specialize this class and consider the sum of local invariants of the specializations, which are elements of the Brauer group of local fields. So by local class field theory, you have identifications of this kind. So there's some, and say V is non-Archimedean, and similarly for real V, there's an isomorphism with the group of order 2 inside Q mod Z, and then you can take the sum of these invariants, and by global class field theory, you must always get 0 if your collection, if your adelic point is in the closure of rational points inside the adelic space. So the bar stays for topological closure. Okay. So we don't need to look into this, but that's how it works. So let me just denote this by let me just do it like this. Sorry. Be the set of elements that are orthogonal in this sense. The Brauer group of X. So orthogonal in quotes means so the sum of local invariants of the specialized element of the Brauer group is 0. So in the example that I'm looking at, this is simply the set of adelic points that satisfy all these conditions for I from 1 to n. Okay. Now that's the simplest explicit description of the Brauer-Manin abstraction, and the result is the following theorem, proved by Tim Browning, Lillian Matthiesen, and myself, for which the crucial ingredient is the work of Green-Tao and Ziegler. That says, in this notation, the set of rational points is dense in the Brauer-Manin set. So the Brauer-Manin set is an open and closed.
All theorems of Colliot-Thélène, which assume Schinzel's conjecture, which is much stronger conjecture, and made such conclusions, that it include this example?
Yes, yes, yes. So exactly, I was going to mention this in a few minutes, that the work of Green-Tao and Ziegler is a substitute for Schinzel hypothesis H in a certain particular case, in the case that I'm talking about here. So when the degenerate fibers are all defined over Q and the ground field is Q. So there's a
Exactly what generality is this theorem? Is this for the specific X?
This is for a specific equation like this. And I'll mention a generalization just a bit later. So X is as above. So in particular, if we remove finitely many primes, so those dividing A, B, and differences of the I and the J, we get weak approximation, something called weak approximation in literature. And again, in particular, rational points are Zariski dense. So is a Zariski dense. Well, in X. So
What does weak mean?
weak means there exists there is a finite set of places such that outside of this finite set of places we do have weak approximation. So that's right. So in particular, rational points are Zariski dense. So you can always find rational points as close as you wish to a given p-adic point. So just clearly, this set is not. So the property cannot be contained in a union of finitely many closed subsets, Zariski closed subsets. So that's So let me just point out that in this generality for such equations, we don't have geometric methods for producing many rational points. For example, we don't know if such surfaces are unirational in general. So geometry is just not able to give results of this kind. So, and let me explain how to deduce this from the results of Green-Tao and Ziegler. Also, let me say which result of Green-Tao and Ziegler I use. So here's so let me start with some algebraic observations. So the easiest possible case of Poitou-Tate duality, which actually can be found in Serre's course in arithmetic, says that this condition, let me call it Bm for Brauer-Manin, well, or maybe product formula, whatever, implies that there exists Ci. So for each I from 1 to n, there exists a Ci, a non-zero rational number, such that okay, so I'm happy to assume that TV is not equal to I somehow, because we can always move point periodically a little bit, and by implicit function theorem. So this is a zero. Sorry, this is one plus minus one, and we have some local. It's locally constant, so we can always move away from the points we don't like. So anyway, it's just more reassuring. So we have such CIs. Okay, and exactly. including the reals. So this means, in other words, that I can find so that means that if I move so everything is up to a square here. So the product Ci and that thing here is a local norm for the quadratic extension given by square root of a. So I can write it like this. Okay, so there exists should I write QV? Sorry. This P must be V. Okay, so I can, I mean, this is the local norm. That's all I say. In other words, we have found periodic points on a certain algebraic variety. So let's consider this variety. And what I've written here just says that this variety has periodic points for all v, and moreover, the value of t is the same as before. So it's given by the adelic point on x we started with. I will need to change this equation a little bit, so I want to homogenize it in somehow, and then I'll write it as t as u over v, and v is going to be a norm like this. So actually, I'm introducing two more independent variables, x naught, y naught, and then let w be the variety given by these equations. Together with okay, so we can eliminate u and v from this equation. So I is ranging from 1 to n. So if we eliminate u and v, we see that we've got a subset of the affine space of dimension 2n plus 2. So it's a section of quadrics of a certain very particular kind. And the upshot of this part of the discussion is that if the original adelic point on x satisfies the Brauer-Manin conditions, then it leads to so if our adelic point satisfies Brauer-Manin condition, then it leads to fiber product of w and x over p1. So the morphism from w to the p1 I'm talking about is given by u and v, and x, as always, morphism given by t. So I mean t's and u and v are related like this. So so somehow what we're doing here is that we are translating the Brauer-Manin condition in a certain liftability property. So in fact, this could be phrased in a more conceptual language at the particular case of descent theory of Colliot-Thélène and Sansuc. So they talk about torsors for tori, and this elementary discussion could be seen as a particular case of the completed general descent theory. But I just want to make this remark and not going back to this later. So, and then it's straightforward to, so since the equation of x was like this, we see that the variables separate. So if we plug in t, so it's u and v, so we end up with something like this. And then a straightforward change of variables shows that this fibered product is in fact birationally equivalent to a honest product of W and a conic. So product of a Q, that is. Okay. So that's a really nice situation, because by Legendre's theorem, C will have a rational point. So this variety has rational points everywhere locally. So in particular, C will have points everywhere locally, and therefore a global point. So you have a rational point. If we can prove that W satisfies weak approximation and the Hasse principle, we are home. Okay. So it remains to prove the Hasse principle and weak approximation for W. Okay, so that's the descent part of the argument. Now I need to recall the result of Green-Tao and Ziegler. So what they prove is generalized, what they call generalized Hardy-Littlewood conjecture in the finite complexity case. Okay, so it's Green-Tao and Ziegler. Okay, so suppose we have n linear forms with integer coefficients. So pairwise non-proportional.
I assume the ends are going to be the same n in
Quite. Yes, it's all tailored to be used in this result.
So I guess n equals 3 could have been done.
Yes, that's correct. That's absolutely right. Yeah. Thanks for this remark. If n is 3, indeed, this is proved by Colliot-Thélène, Sansuc, and Schinzel in the 1987 paper. Actually, they prove a more general result. They prove result of any number field, and in the case when degenerate fibers are not necessarily defined of this ground field. So I mean, they have a more general case, but only provided n is small enough. So n is at most 4. There isn't circle method. No. There is well, I mean, the only analytic tool I think they use is the Dirichlet theorem on primes and progression. No, there's no circle method there. There's something similar.
This corresponds to the U2 now.
Sorry? Ah.
Equals 2 corresponds to what Gauss calls the U2 now.
Possibly.
Completely elementary.
Yes.
This is the time of whatever.
Yes. Okay.
Vinograd.
Ah. Okay. Well. All right. So pairwise non-proportional. yeah, there was a competing result of Hugh Brown somehow very similar. And anyway, so linear forms, and so let's yeah, we also have n integers c1, cn, and then okay, I need to continue somewhere. So we have a periodic assumption. So let's assume that for any prime p, there exists a pair of integers. Sorry for the same. It's not the same n. I mean, it's just. Well, I should. It doesn't matter. Okay. Such that p does not divide for all I. Okay, so it just says that this polynomials, this polynomials of degree 1, li plus ci, I mean together, they don't have some silly properties. We want to avoid some unlucky.
Like degenerated twin Brown.
Quite. Exactly. And then let k in R2 be an open convex cone containing a point for which the value of this linear form is all positive. So all these linear forms, some positive. Okay, we're going to look for pairs of integers mn such that the values of such linear polynomials are going to be equal to prime numbers. So clearly there must be some real condition like this. So there's one periodic condition, one real condition, and then the conclusion is then there exist infinitely many pairs Mn in this cone such that
I think probably you don't need the risky density stuff. They certainly prove it. I mean, they prove much more than that.
yes, yeah, oh yeah, there's some formula exactly.
You need the risky density or just infinity?
For this, we just need infinity. No, we just need this.
For you,
Just this. Oh, this is the wonderful theorem, which is an amazing and complicated result, and an easy corollary that will be handy for the Hasse principle on W is.
So I guess what Colliot-Thélène was doing, he was using one variable only, probably, when he used Schinzel Harpaz.
Quite, absolutely, yes. So corollary, which is straightforward to deduce from this result, so I will not give details. I mean the elementary. So given a collection of pairs of periodic numbers where P is an element of a finite, so S is a finite set of primes, and a positive constant C and also U1 En pairwise different rational numbers, which will assume that are elements in Zs. So this is Z localized in S. We allow denominators which are products of primes from S. And then the conclusion is there exist infinitely many pairs of integers, basically. Again, we allow denominators in S. And pairwise different primes such that first there's a real condition, so lambda and mu are positive and lambda divided by mu is large. Second, for primes in S, lambda mu is very close, as close as we like. To lambda pu mu. Okay, and most importantly, lambda minus ei mu is almost prime, so it's pi times ui, where ui is a rational number such that both numerator and denominator are only divisible by primes from S. So it's essentially prime outside this fine set of bad primes S. Okay, so now the proof that W satisfies the Hasse principle is, in fact, not hard at all. So we start with some periodic points and the real point. So for each p, we're given a periodic point on W, and m naught will denote a real point. And so it will have some coordinates u and v. Now we can just modify it a little bit, assume u and v are both rational numbers, and then change variables so that we can send this point on P1 to any point at P1, for example, to infinity. So we can assume that without loss of generality, this point is given by 1, 0, and then some x's and then some y's. So this is u and this is v. So I'm talking about the real point. All right, so we increase, if we have to, the set of primes, where we also will need to prove the weak approximation. So we're given some set of primes. We can increase the set as much as we like to a larger finite set by including into it the primes dividing, all primes are beta reduction essentially. So primes dividing A, dividing the differences EI minus EJ, and dividing CI, so all the numbers that are in the picture. Essentially this is just a one reciprocity argument now that remains. Maybe I'll do it on the other board. Okay, maybe. Can I write here, or is it illegal? I shouldn't. I will, but I'm okay. Good idea. So what do we have? We have so let me use lambda and v, sorry, lambda and mu for, so lambda p, mu p will be uv coordinates of mp, okay? So these are, so we know that mp is a point in w, so sorry. So we know that this is a local norm. Well, local norm for the extension when p is in S for all I. Okay, that's because that's just a point on my variety. That's a consequence of the equation of the variety. So that's all right. Now, and what we want, obviously, is to show that if we take lambda and mu provided by this corollary, we want to show that this is a global norm. Okay, that's the, if we show this global norm, we win. So let's use the product formula. Okay, let's use the product formula, so which says that 1 is the product of Hilbert symbols for all v. So yes, you're right. Yes, because I also have this equation, but it's just not different from the rest. Yeah, you're absolutely right. Yeah. Well, actually, I think it's automatic because the one last equation will be like this. So it's there is no constant there. So just it's because my last equation was so there's the it's okay. I mean, it was just given like that. I mean, I've chosen v to be of this form. Yeah, so it's always form. So it's not a worry. Okay, so I'm fixing I, and the product formula gives me that the product of all Hilbert symbols is 1. In fact, I know that for v in S, the finite set, it's 1 already because lambda and mu are very close to lambda p and mu p. So by continuity, we're okay. So I write p naught in S. Well, v naught in S. Next, if v is not equal to pi, I know from this last condition that lambda minus ei mu is in fact a unit. So this guy is a unit outside S and pi. And so is A, because I included into S all primes that divide either numerator or denominator of A. So this, so outside of S, provided V is not pi, there are this and this are both units. So the Hilbert symbol is again trivial, again 1. So I end up with just one Hilbert symbol, and that is for pi. And so by reciprocity, by the product formula, this must be equal to 1. And therefore, so equals 1. And therefore, Ci lambda minus Ci mu is a local norm everywhere, and hence a global norm. hence globally. Okay, and we're done. Because we found a rational solution to our system of equations. So this proved the Hasse principle for W, and weak approximation is easy. So just using okay, let me just not mention. So that more or less concludes the proof of the theorem of Browning, Matthiesen, and myself. So let me just mention that this proof that W satisfies the Hasse principle, this elementary proof, was found in another paper, the paper by Harpaz, Wittenberg, and myself, because originally we used the results of Matthiesen from her thesis in Cambridge, which was sort of independent additive combinatorics work that used Green and Tao, but somehow was monolithic. Now this is rather short. Anyway, let me now mention how this kind of results can be generalized. So if you use a little just a tiny bit more machinery, some cohomological, I don't know, just a bit of cohomology will give the following results. So, but also crucially, it requires slightly stronger result from additive combinatorics. So let me state the theorem. Let T be a torus, an algebraic torus of a Q, and let X be a variety smooth proper geometrical integral with a surjective morphism to the projective line of a Q, satisfying the following condition. Okay, surjective morphism. So first, the generic fiber is a principal homogeneous space of the field of rational function in one variable for the torus T. Secondly, there exists a finite. Well, the second equation basically says that the bed fibers are all other Q rational points of P1. So in other words, there exists a finite set E of rational numbers, basically, such that if I throw away the fibers over points of E, then I get a smooth morphism. And then the conclusion is that every point, or that the closure of rational points in the adelic points coincides with the Brauer-Manin set. So you can see this obviously a generalization of the equation I started with. So for such varieties X, the topological closures of rational points in the adelic space is the Brauer-Manin set. And, well, clearly, I mean, you can write examples of this situation. So, for example, let me use the following notation. So if K is a number field with basis omega 1 omega r, so I'll write the norm form sorry, R. Okay, it's just notation. So, and then we can consider, so an example of this situation, example of such a variety X could be varieties given by the equation of the form. So if we have finitely many number fields, we can sort of look at the corresponding norm form, well, possibly raise them to some powers, and let this equal to some totally split polynomial with of rational numbers. Okay, so of course I need to make sure that I have a torus, so I'll assume that highest common factor of B1, Bm is 1. Okay, and then as before, B is a non-zero rational number, and EJs are pairwise different rational numbers. So, I mean, such equations give example of this result. Now, I mentioned that I need slightly stronger analytic ingredient. So this is based on the work of Browning and Matthiesen that use additive, who use additive combinatorics. So, I mean, the scheme of proof, the sketch, I mean, the idea of proof is the same as before. Just you need to work slightly more. I mean, all this explicit change of variables will have to be replaced by some cohomological arguments, but they are not difficult. So the analytic ingredient is again the Hasse principle and weak approximation for the analog of the variety W, which in this case will be given by equations like this for.
In all these, the most important thing is the two variables u and v.
Yeah.
Right?
Yep. There's.
And that's because you're looking at rational numbers. That if you're two integer variables, well, I guess just going back to Colliot-Thélène, if you wanted to make those integers, he could get that for each fixed you know what.
Yeah, there's this fantastic. Yeah, there's this tremendous difference between one variable and two variables. You have to make sure that you work with two variables. Yeah. I mean, student and I always insisted that the right approach must be with two variables, not one somehow. So, but it just makes certain things less clear. But that's the way to make things work. Yes, that's right. Right now, well, I think I need to.
But they didn't have to do anything new in the Green-Tao-Ziegler work.
No, this is well, I'm unable to comment on their work, but this is additive combinatorics. So they.
What did they do that?
The papers in the archive, I don't know. I mean, they really used Green-Tao and Ziegler. So,
I mean,
what is?
About linear equation, as long as you have two more.
You need a rank 2 group.
You need what?
You need rank 2. Right? You need two variables.
Two variables, yeah, but they always have two variables. I'm just, is there a theorem that they have there that's a new purely prime theorem about prime?
I don't know. I can't answer. Sorry. Well, I think I need to finish soon. Let me just mention that there is a different method to approach the same problem. So instead of looking at basically torsors for tori over X, or some larger varieties of high dimension that maps to X, you could fiber X. So in these examples, X is always a one-parameter family of some variety. So there's something called fibration methods so it's aiming to show that we can find a fiber with a rational point. So maybe just mention what comes out of this. So there's a sort of competition of these two methods, which are not quite equivalent somehow. So results are available in which you don't expect this separation of variables. You don't. I mean, like in this case, in the end of the day, you have the same phenomenon that after descent, this auxiliary variety you get after descent will be birational equivalent to a product of W and something you can work with, like a principal homogeneous space for T. Now, in general, when you don't have this sort of rigid structure, when there isn't a torus with such properties, but you have a family of, I don't know, like quadrics, for example, of dimension 2, or maybe severe Brauer varieties, which is not as, which are not principal homogeneous spaces for a constant torus, so to say. But torus could be variable or something. Anyway, the results are available. Let me just quote what you can obtain in this way. So fibration method is a different method, which I unfortunately don't have time to explain. Will give same result for families of quadrics or severe Brauer varieties satisfying the same condition that the variety is defined over Q and the bed fibers are all over Q. Well, maybe I just mentioned as before. So there's potential for more generality here. So there's, I think Olivier Wittenberg and Jonathan Harpaz are working on a better result. So I expect that one will be able to treat cases when the fibers are not assumed to satisfy the Hasse Prince-Weak approximation, but maybe just satisfying the condition of this kind. So that's entirely possible. So, and finally, I would like to yes, okay, we discussed already that this fibration method is exactly what was used by Colliot-Thélène, Sansuc, and their co-authors to prove conditional results based on Schinzel hypothesis. So Schinzel hypothesis H is like a wild generalization of Dirichlet theorem on primes and progression, where you replace a linear polynomial by a system of polynomials of not necessarily linear. So in the case when polynomial is actually linear and the ground field is Q, Schinzel hypothesis can be replaced by Green-Tao and Ziegler. So many results now become unconditional. So finally, let me finish with a negative result that says that, okay, now we sort of understand better what happens for black one. That seems to be appropriate. Yes. So I would like to finish with this with a counterexample. So this cannot be generalized. This kind of result cannot be generalized to base curves of higher genus. I mean by this that if you have X equipped with a morphism to some curve E, which is, for example, an elliptic curve or a curve of higher genus, then you cannot explain, so they cannot expect anything of this kind. So in a recent paper by Colliot-Thélène, Ambrose, Paul, and myself, we use one trick of Bjorn Poonen, who suggested to work so that the worst possible situation is when you have a curve with just one rational point. So that was Bjorn's idea. So suppose that E is a curve, of genus 1 or higher than 1, that has exactly one rational point, then it's very easy to consider examples when everything breaks down. Namely, think of the following situation. So suppose that x to e has fibers. This was an example. Exactly. Yeah. So this. Yeah. So we have an example when x has no rational points, and yet the corresponding Brauer-Manin set is non-empty.
All kind of generalizations or variations on Brauer-Manin.
I'll tell you exactly what I mean. So I'll just give one example. Yes, actually, yeah. Okay, this right, and also there was there was some interest in considering some generalizations of Brauer-Manin abstraction where you apply the Brauer-Manin conditions to finite total coverers of X, and this also doesn't help. So nothing helps. It's completely desperate. So the situation is then the fibers are two-dimensional quadrics. It's very easy. It could be explained in 3 minutes. With mild generalization, so with sort of degenerate fibers of rank 3. So the bad fibers can be just so it's a good fiber, and the bad fiber could be a cone over a conic, but not the union of two planes. So here's what I suggest to look at. So let's assume for simplicity that the base curve is an elliptic curve. Say the real set is real locus is connected, so that's a real locus. That's my. So suppose this curve has just one rational point, and the fiber over this rational point is a smooth quadric which has points in all periodic fields, but no real points. Okay, there's plenty of such. And suppose that if you move a little bit along the real locus, you meet, there's a degenerate fiber, which is like this, and then further down there's another one, and the set of real points of the threefold, so actually the threefold, will be some domain like this. Okay, that's a set of real points. The image is this closed interval. Okay, so the idea is to take the adelic point, consider the adelic point such that if p is a prime number, take MP in the fiber over 0. So 0 is this point. For all primes p, and then take any real point where you can find it. Now, obviously, this threefold contains no rational points, because all rational points must be in the fiber above the unique rational point on the base, and there is no real point in the fiber. But if you take an adelic point of this kind, so we can show that this adelic point satisfies all the Brauer-Manin conditions. So let me find another blackboard. So in fact, one shows, so this condition that because we have such mild degenerations, what we have is that pi upper star, so the induced morphism in the Brauer group, is a surjective homomorphism. I mean, that's elementary. It's basically because the Brauer group of the general fiber is all coming from the Brauer group of field of functions on the base. So and there are no I will have problems if I had degenerations into union of two planes, but I have no such thing. So that's why I have this. Okay, let me not explain any further. And therefore, so any element of the Brauer group of X will be coming from the Brauer group of E. So they all be pi up a star of A for A from the Brauer group of E. So I need to evaluate that thing on my local point. So if I do this, then clearly it's the same as A of 0, and I can normalize A. Let's assume that A at 0 is 0. So by modifying A by a constant element of the Brauer group of Q, which play no role for the Brauer-Manin abstraction, I can assume this is 0. So let's assume this, so that there's 0. And then the real point is also 0, because this will be the value of A at the image of M0. But it's path connected. This projection here is the same connected component as 0, and everything is continuous. So it's also 0. So the sum of zeros is 0. So Brauer-Manin gives strictly nothing, and there's no hope even after finite total covers. So I don't want to finish on a negative note. Let me just mention that maybe in general, if you want some result that works for arbitrary varieties, you should be asking about 0 cycles of degree 1 rather than rational points. And then there is hope, because Colliot-Thélène made the conjecture of the Brauer-Manin condition that can be also defined for 0 cycles of degree 1 for our arbitrary variety. It should be enough always. So in other words, if you have a family of 0 cycle degree 1 of periodic fields, and such that together they satisfy the Brauer-Manin condition, there must be a 0 cycle degree 1 of a Q. And there is the same work which I want to advertise, this work by Harpaz and Wittenberg. They proved some result of the kind, if you have this for fibers, you have it for the total space under appropriate conditions. So I'd like to stop now. Thank you.